Hi, this is Schwartz from MasterMathMentor.com. This is video AB Review 3. The topic is exponential functions and logarithms. It covers the AB manual, page 273. When you were in grade school, you first learned addition. But subtraction was harder. Some teachers try to explain subtraction in terms of inverse operations, although they never actually stated that. So for a student struggling with 9 minus 4, the teacher might ask, what number do you add to 4 to get 9? And like magic, students quickly come up with the answer of 5. The same is true with logarithms. The statement y equals b raised to the x and x is equal to log base b of y are equivalent, just like 9 minus 4 equals 5 is equivalent to 4 plus 5 equals 9. So to find log base 2 of 32, we call it x, and therefore we can write the statement as 2 raised to the x equals 32. And most students will quickly answer that x is 5. So to find log base 5 of 1, we set log base 5 of 1 equal to x. And therefore 5 to the x is equal to 1 and x is equal to 0. The log of 1 with any base, as long as the base is positive, is always equal to 1. So to find log base 3 of 1/9, we set it equal to x, and therefore 3 raised to the x is equal to 1 over 3 squared, and therefore x is equal to -2. To find log base 8 of 4, we set log base 8 of 4 equal to x, and our resulting equation is 8 to the x is equal to 4. We will write each expression as powers of 2. 2 raised to the 3x is equal to 2 squared, and therefore 3x is equal to 2, and x is equal to 2/3. If no base is given, then the base is assumed to be base 10. So y equals 10 to the x can be expressed as x equals the log of y. Y equals e to the x can be expressed as x is equal to ln of y, where ln is called the natural log with base e, the irrational and transcendental number approximately equal to 2.71828, ... So when asked to find the log of 100, we set it equal to x, and therefore we are solving the equation 10 to the x is equal to 100, and therefore x is equal to 2. When finding the natural log of 5 on your calculator, you are actually solving the equation natural log of 5 is equal to x, and therefore e to the x is equal to 5. Obviously, x will be irrational. We see the graph y is equal to 10 to the x in red. It passes through the point 0, 1. The domain of this function is negative infinity to infinity because we can take 10 to any power, positive, negative, or 0. But the range will be 0 to infinity because 10 to any power will always be a positive number. We also see the inverse of 10 to the x, which is y is equal to log of x in blue. And the domain of this function will be the range of the 10 to the x function from 0 to infinity. We can take the log of any positive number. The range of the log function will be the domain of 10 to the x, negative infinity to infinity. When we take the log of any number, we can get a negative answer, a positive answer, or 0. There are 3 rules that students must always keep in mind. that will simplify problems involving logs and natural logs. These rules work with logs of any base, including natural logs. First, the log of A plus the log of B is equal to the log of A times B. Secondly, the log of A minus the log of B is equal to the log of A over B. And third, the log of A raised to the B power is equal to B log of A. Let us see some examples of these rules in action. In problem 1, we have 6 expressions. We will use our log definitions and log rules to find their value. In A, we have log base 4 of 8. We set that equal to x and then write the equation 4 raised to the x is equal to 8. Writing everything with a power of 2, we have 2 raised to the 2x is equal to 2 cubed, and therefore x is equal to 3/2. We can also say that log base 4 of 8 is log base 4 of 2 to the third. We can bring the 3 in front and write that as 3 log base 4 of 2. Log base 4 of 2 is 1/2 because 4 to the 1/2 power is 2. So this is 3 times 1/2 or 3/2. In B, we're asked to find the natural log of the square root of V. Again, we set that equal to x, and our resulting equation is e to the x equals e to the 1/2, and therefore x is simply 1/2. Or we can write this as natural log of e to the 1/2 and bring the 1/2 in front and write this as 1/2 natural log of e. Natural log of e is 1 because e to the first is e. So this is 1/2 times 1 or 1/2. In C, we're asked to find 10 raised to the log 4 power. We don't know what log 4 is, so we will call that x. And therefore, our resulting equation is 10 to the x is equal to 4. However, that is what we're being asked to find. 10 to the log 4, which is 10 to the x, and therefore our answer is 4. This is occurring because 10 to a power and log are inverses and cancel each other out. We start with 4, we take its log, and then raise 10 to that power, we will end back at 4. D reads log of 2 plus log of 50. To find the log of 2, we would have to solve the equation 10 raised to the x is equal to 2. And our answer would be irrational and not easy to find, except with a calculator. The same is true with log of 50. However, we can use our log rules to write this log of 2 plus log of 50 as log of 2 times 50, which is log 100. And the log of 100 is 2 because 10 squared is 100. E reads log base 4 of 192 minus log base 4 of 3. Each of these logs would be impossible to find algebraically. For instance, there is no rational number such that 4 raised to the x power is equal to 3. But again, we can use our log rules and write this expression as log base 4 of 192 over 3, which is the log base 4 of 64. And we know that 4 raised to the third power is 64. So log base 4 of 192 minus log base 4 of 3 is 3. F reads natural log of the fifth root of e to the third. We can write this as natural log of e raised to the 3/5 power. And using our log rules, we can write this as 3/5 natural log of e. The natural log of e is 1, and therefore our answer is 3/5. In problems 2, A through C, we have 3 equations involving logs. we can use our log rules to find the algebraic answer to each of these problems. In 2a, we have log base 9 of x squared minus x plus 3 is equal to 1/2. Writing the problem exponentially, we have x squared minus x plus 3 is equal to 9 to the 1/2, which is 3. The 3's cancel, we can factor and write x quantity x minus 1 is equal to 0. And therefore x is equal to 0 or x is equal to 1. We must check our answers to make sure we are taking the log of positive expressions. When x is equal to 0, we are taking the log base 9 of 3, and when x is equal to 1, we are also taking log base 9 of 3. So this problem has two solutions. In B, we have log base 36 of x plus log base 36 of x minus 1 is equal to 1/2. We will write this problem exponentially using our log rules. Log base 36 of x times x minus 1 is equal to 1/2. And we can now write this as x times x minus 1 is equal to 36 to the 1/2, which is 6. Bringing everything to one side, we get x squared minus x minus 6 is equal to 0. Factoring into x minus 3, x plus 2 is equal to 0. However, this problem only has a solution of x is equal to 3. When x is equal to negative 2, we are taking log base 36 of negative 3, which does not exist. C, we have natural log of x minus natural log of x minus 1 is equal to 1. Using our log rules, we can write this as the natural log of x over x minus 1 is equal to 1. And writing this exponentially, we get x over x minus 1 is equal to e. Cross multiplying, we get x is equal to ex minus e. And solving for x, we get all the x's to the left side, and we get x is equal to e over e minus 1. We need to check our answer. This e over e minus 1 is a number greater than 1. And when we check, we find that when we take the natural log of x or the natural log of x minus 1, these values exist when x is equal to e over e minus 1. 2, d through f are exponential equations, and while we could solve these graphically, let's solve them algebraically. In d, we have 5 raised to the x is equal to 20. The way we solve this is to take the log of both sides, or if you wanted to, the natural log of both sides. We get log of 5 to the x is equal to log of 20. We could use our log rules now to write this as x log 5 is equal to log 20, and therefore x is equal to log 20 over log 5. You could also say x is equal to the natural log of 20 over the natural log of 5. Don't make the mistake of thinking that the log of 20 over the log of 5 is the log of 4. It doesn't work that way. In e, we have e raised to the negative 2x is equal to 5. We treat this the same way. We could either take the log of both sides, but here it's easier to take the natural log of both sides. We get the natural log of e to the negative 2x is equal to the natural log of 5. Using our log rules, we get 2x natural log of e is equal to the natural log of 5. And the natural log of e is simply 1. So 2x is equal to the natural log of 5, and x is equal to the natural log of 5 over 2. Note that this answer, natural log 5 over 2, is not the same as log 5 over 2. The reason is, even though we can take the log of both sides, when we take the log of both sides, we would also have the log of e. When we had the natural log of e, that was 1. But log of e is not 1. So be very careful. They are not interchangeable answers. In f, we have 2 raised to the x is equal to 3 raised to the x minus 1. To do this, we will take the log of both sides and get the log of 2 to the x is equal to the log of 3 raised to the x minus 1. You could also take the natural log of both sides. We get x log 2 is equal to x minus 1 log 3 by using our log rules. Multiplying out, we get x log 2 is equal to x log 3 minus log 3. Getting to the x's to the one side, we get x log 3 minus x log 2 is equal to log 3. Factoring, we get x times the quantity log 3 minus log 2 is equal to log 3. And our final answer is x is equal to log 3 over log 3 minus log 2. We can check this problem graphically if we wish to, or we could find the value of log 3 over log 3 minus log 2 and determine if 2 raised to that power is equal to 3 raised to that power minus 1. Finally, don't make the mistake of saying log 3 minus log 2 is log 1. It doesn't work that way.